everyone. My name is Qian. I'm an assistant professor at the University of South Carolina. It is a great pleasure to participate in this year's Crosstie and Fastening System Symposium. Today, we would like to present some work we did in the intelligent railroad track component inspection. I would like to acknowledge my PhD student, Mr. Feng, for his great contribution in this work. This presentation is organized in 3 parts. First, I will introduce the background and motivation for our research. Then I'll give you several examples of different projects we worked on before. And also at the end, we'll talk about what are the current and future studies. We all know track needs to be maintained to ensure safe and smooth operations. That is actually true for anything we have. Anything need to be maintained in order to ensure it's in good condition. So what is exactly need to be maintained for the railroad track? Of course, the different components, right? For example, the rails, the ties, clips, pads, spikes, ballast, etc. If we do not maintain them well, we will have problem with the track. So that is the reason FRA also requires mandatory track inspection on different track components. In order to inspect them and assess their condition in an efficient way, we need accurate yet efficient track component inspection system. Different systems with different purpose have been developed over the years. For example, the ground penetration radar system in order to assess the ballast conditions. The ultrasonic test in order to detect any internal flaws of the rails. The laser sensors used to measure the track geometry and also detect any obstacles along the track. And also recently drone has become a popular platform to serve for different purposes. Those inspection systems have greatly helped us to inspect different components. There are still some challenges remain in the track inspection work. For example, 2 challenges I can think about right now are the inspection frequency and the data processing time. Because often it requires expensive equipment and also substantial amount of training for the technician who can operate the equipment. Different equipment may also require different amount of track time. These factors all limit the track frequency. Inspection frequency, and also the data processing need time. Often the data collected in the field need to be transferred to a lab to do centralized data processing. So there will be a reporting lag between the time the data is collected and an issue is identified, if there is any. So we can do a simple Google search, try to see if there's any accident related with component failure. It's not typical to find some. You can see for the past several years, we can find some accident that happened. It can be related with different component failure. For example, the broken joint bar, the broken spikes, missing spikes, and also some other failed fasteners. Those accidents don't mean the railroad did not inspect their track. It's actually related with the challenges I mentioned on the top. So the inspection frequency and the processing time that is needed to process the data. Okay, so our research motivation is actually related with the missing spikes. We have a side project that to develop a laser-based non-destructive spike defect inspection system. So basically what we try to do is to send a laser excitation to a spike and to listen to the reflective signal to identify if the spike has a defect or not. So first thing first, we need to identify and locate that spike. So then we can send the laser excitation, right? So how can we do that? How can we locate a spike automatically and quickly? Or how can we identify any track component automatically and quickly? So that is actually related with the component inspection. Recently, the artificial intelligence-based computer vision has paved the way for us to identify and locate any component we want. In fact, the AI technology has been developed so quickly and has been quickly adopted by different engineering disciplines to serve different purposes. For example, to identify the pedestrians, vehicles, pavement cracks, railway components, aircrafts at different locations. So this is the foundation. We continue our work. So in order to identify the track component we want and locate them, we developed an automatic railway track component inspection system using real-time instant segmentation technology. So basically, we developed a model based on a fully convolutional neural network, which includes backbone, feature pyramid network, protonet, and the prediction head. So the input features from a given image can be extracted by the improved backbone, and the FPN structure is responsible for detecting objects at different scales. To be more specific, our contribution is to let one single detector to detect the components that are having significant different scales. For example, the rails are quite different in terms of size from a spike from the top view of the track. To improve the operation speed of this model, instance segmentation is achieved by two parallel tasks in the original and our improved model. So one of the parallel tasks is to generate the prototype masks. This is completed by the protonet. The prototype is shown on the left side of this slide. With those prototype masks, the computation cost can be significantly reduced. The right part of this slide shows the data preparation with label me and the loss function for evaluation. This slide compares the training performance between the original model and our improved model. Basically, the top row figures are from the original model, and the bottom row figures is the results from our developed model. High area corresponding to high recall and high precision for each class. High precision indicates the detection has more relevant results than the irrelevant cases. And a high recall means the model returns most of the relevant results. So the evaluation matrix is the IOU. Basically, our predicted and located component has a certain amount of overlap with the ground truth. If the IOU equal to 0.5, 50%, that means our predicted and located component has at least 50% with the ground truth. The 75%, the IOU indicate the predicted and located component has at least 75% overlap with the ground truth. So it's easy to see with the 75 threshold. For example, our model has outperformed the original model quite well. The figures on the previous slide may be a little bit too abstract to understand. Hopefully the pictures provided in this slide is a little bit more straightforward. Okay, let's focus on the left side of this slide first. The first row indicates the ground truth. So the picture on the first row, most left column is the original picture. Okay, and for row 2 to row 6, that are from different models. The row 2 is the model we developed. Okay, and from row 3 to row 6 are the results from different state-of-the-art computer vision models. Okay, so that's the difference between different rows. So what about different columns? If you see the title for the different columns, that are different lighting conditions. So we think the detection accuracy will be impacted a lot based on the illumination conditions. So we manually reduce the brightness in order to illustrate the sensitivity of the illumination conditions on different models. Okay, so you can see different models have different performance. Sometimes a certain model may miss a certain clip. Sometimes another model may miss another spike. Okay, I want to point out, if we look at the last column and the first row of the figure, okay, you can see it's very dark. It's even difficult for our eye to identify any components from this picture, maybe just the rail, but you can see some models actually performed well, especially our improved model. And the right hand side of this slides actually let you know the detection accuracy of different models. For this slide, I just want to give you an example to show how this model actually works. So basically, this is a video we shoot from our smartphone and process it simultaneously. So you can see as we're walking by and shooting the video of the track, we can successfully identify those track components and put a colored mask over it. This model we actually only use a single detector to detect the multi-class objects. What that means is you can see the rails, the clip, and the spikes actually are quite different in terms of area that occupied from a single frame image. Okay, and also we achieved the processing speed or the inference speed of 30 frames per second. That's actually a threshold to determine whether this is a real-time segmentation model or not. We actually did that. But to continue our research, we need to ask ourselves, can we make that faster? What about if there's any change? Okay, so basically, can we identify the change if a spike is missing? If a clip is broken, if there's a crack on top of the rail or not. With those questions to ourselves in mind, we extend our research. And this work has been published in the Automation in Construction, and the link to that paper is provided on top of this slide. So basically, we try to make our model better in terms of speed and also to detect any change. After finishing our previous work, we're wondering if we can improve a model that can significantly improve the detection speed, so it can work with a narrow inspection time window for the track component inspection. So inspired by the newly released ULV4 framework, we improved it with a simple but very efficient way. So we have 3 different detection scales, including large scale 64 by 64, a medium scale 32 by 32, and a small scale 16 by 16. Were designed in the detection head for coping with different instance size. If you still remember, right, the rail, spike, and clips, they are in quite different size. So how can we tailor the model in order to detect them efficiently? Of course, we also put some other tricks. For example, we use the PA net as the net component and SPP model to improve the lateral connections between the backbone and the neck in the network. A tricky part in the computer vision, especially in the neural networks, is the activation function. It is a critical part of the neural network and has proven key to high performance among a wide range of tasks. It determines whether a neuron in the neural network should be activated or not. Okay, and it's characterized by a variety of properties. For example, the derivative, monotonicity, etc. for customized training. So in the training phase, we try to find a suitable activation function to let that meet and tailor that for our inspection tasks. So by doing that, we can keep a high computing efficiency and also maintain the high accuracy for the component we try to detect. So basically what we did is try to develop a customized hybrid activation function that is shown in figure A. Figure B and C are 2 classic activation functions, and figure D and E are the ULV4 and ULV3 with the original activation function. So you can see the hybrid activation function actually outperforms all the other models. That proves the work we did helped to improve the model in terms of accuracy and the efficiency. This slide summarizes the evaluation metrics values together in order to compare the performance of different models. As shown in this table, you can see our developed model ULV4 hybrid can maintain a high accuracy, while the inference time can be increased to close to 80 frames per second. That means if we have a camera that can take 80 frames per second, the processing time is real time. So whenever there's a new frame come into the model, it will be processed right away without extra buffering needed in the memory. So after we convinced ourselves the ULV4 hybrid outperforms several other activation functions that can be integrated with ULV4, we further trained our model and also some other state-of-the-art models to compare the performance, including the popular Fast RCN, RetinaNet, Mask RCN, so on and so forth. So you can see the model we developed actually outperforms all the models that are popularly used in the general detection purpose. These slides give you an example from a specific frame to show the performance between different models. So you can see the red arrows indicate the missed detection. Basically, the model failed to detect anything. The ULV4 hybrid, the model we developed, did not miss any clips, spikes, and the rail. But some other state-of-the-art models may miss a clip or a spike somewhere. To increase the detection speed is not our only interest. As mentioned earlier, we also want to see whether our model can detect any track component status changes or not, whether there's a new piece, whether there's a missing piece or not. So this slide presents the work on that part. The left column's figures are the original images, and the central columns are the detection result with the original images. The right columns shows the detection with some changes. For example, for the first row, we can see one of the two spikes is actually replaced by a piece of rock, and the model did not identify the rock as a spike, although it looks very similar to a spike from the top view, and it was put exactly at the same location. For the second row, if we compare the images, we can see there's an extra spike put into the tie, and the model successfully identified as an extra spike. For the bottom row, we can see there's one clip was missing. So the model successfully understand it and only labeled 3 clips instead of the original image with 4 clips. So it looks like our model is fairly promising. So we showed the status changes of the spikes and the rails. Some of you may ask, okay, what about the rails? Okay, so we also think about that question. So we continue our work to see if there's any change of the rails we can detect. The third example I'm going to show is another model we developed to automatically identify any real surface defects. This work has already been accepted by the Transportation Research Report, and I will share that paper with you once it is published. Due to the nature of the surface defect showing in an optical image, here we select the mask RTNN architecture as our main structure to work with. More specifically, there are 2 parts are included in the structure. The backbone for the feature extraction over input image to generate feature maps, and the prediction head for bounding box generation and a mask generation. These slides quickly show you the result of the defect identification and quantification, regardless of the image orientation. And no matter how severe the defect will be, we can also identify them and label them successfully. One more question would be, what about I cannot take images from a perfect angle? or I want to collect images very quickly. So actually that was related with our current, which is a UAV-based automatic real surface detection, defect detection system. So instead of using a camera held by our hand to take image one by one, we can use the UAV just to fly on top of the track and let it to record the videos. Of course, if we record a video by the UAV, we cannot guarantee all the angles and the height from the track is a fixed number. There's always some variations due to the wind and the speed of the UAV. Here, just show you a quick result of the model we developed and compared with the state-of-art models. The RBGNet is the model we developed, and the last column, GT, stands for the ground truth. So you can see from this figure, we can successfully segment the rails very well. Another ongoing work we are conducting right now is to develop another model for the automatic overhead catenary defect detection system. So basically, we not only focus on the component that is underneath the train, but also the component that is above our head. The challenges existing in this work is the number of effective pixels, because we take the images of the entire catenary system. So some of the tiny components only occupies a very, very limited amount of pixels. Some of them only have 20 pixels, 50 pixels, although the entire image may be a 2K image. So this is something we're doing now. At the end, I would like to acknowledge the National Academy of Science and the FRA for supporting our work, and also our industrial partners CSX and Norfolk Southern for their help for different works. Thank you very much for listening, and I appreciate your time with this presentation. If you have any questions or comments, please feel free to contact me. I provide my contact information here. Thank you again. I hope you enjoy the symposium.